Well, good morning. Welcome to our next lecture. And so today will be about holographic superconductors, and we'll be building an ADS phenomenological model which recovers, the behavior of superconductors. And you will see that's a very, very simple model. And again, you can do some cool stuff on the CFT side or on quantum field theory side by doing a very simple gravitational physics calculation. But before we jump into the ADS description, let me just do a lightning review, which will probably take most of the lecture, of normal superconductors. Okay, and so normal superconductors, they have two basic features. So one of them is that the DC conductivity actually diverges. So DC means that you are taking omega goes to zero. So at zero frequency, there will be a diverging conductivity. So I just remind you that there is something which is called Ohm's law. So the current is given by conductivity times the applied electric intensity. So if you have diverging conductivity here, you can have current even if there is no external electric field, or you can have infinite current if there is an external electric field. But basically, it doesn't take any energy, doesn't take any force to move to induce the current there. There is another feature. So this thing here would be also true for perfect conductors. Okay, but the second feature is really the thing which distinguishes the two, and it's called Meissner effect, and it tells you that the magnetic field is expelled from the superconductor. So whereas in perfect conductors you can have constant magnetic field, so here really the magnetic field is zero inside. Right, so everything is expelled, and then you have these cool experiments of levitating frogs and stuff like that. Very cool feature. So now if you actually look at what's happening more precisely with this conductivity, then at zero frequency, you really have like an infinite conductivity. And then if you move away from this omega equal to zero, there is basically zero conductivity, the real part of that, until you increase frequency so much that there can be some thermally excited electrons, and then your conductivity, the real part of the conductivity again starts increasing. But basically there is like a huge gap, and it's the delta function for the real part, and then you can have some thermally excited electrons and stuff like that. On the other hand, the imaginary part of conductivity, so conductivity is a complex number, so the imaginary part goes like 1 over omega, and so this is that. So now there is something which is called Kramers-Kronig relations, and they basically interrelate these real and imaginary parts. And if you look at the formula over here, so this is the principal value of the integral. Imaginary part is given by some integral over the real part. So if I take my real part to be delta of omega, then this integral is very easy to do. It just picks up 1 over omega up to a sign, well, whatever. So you see that the delta omega for the real part corresponds to 1 over omega of the imaginary part and stuff like that. So basically, if you discover that there is a pole in the imaginary part which goes like 1 over omega, you know that already there will be this infinite DC conductivity and stuff like that. And so why I am saying this is that, of course, people study these things numerically on the ADS side. And so it's very difficult to identify that you have discovered a delta function, right? So that's very difficult. On the other hand, to discover 1 over omega pole in the imaginary part is reasonable numerically. I can start plotting this thing here, and so this is easier. To identify numerically. And so for this reason, people take this 1 over omega behavior of the imaginary part of conductivity as a sign that you have infinite DC conductivity and stuff like that. Are there any questions about this? All right, so now let me continue this lightning overview with these superconductors. And so microscopically, we will not care about microscopics, but microscopically, these superconductors are described by the BCS theory, Bardeen-Cooper something, BCS theory. And the construction is really cool in the sense that somehow you force your electrons to like each other, and so these electrons start forming Cooper pairs. So there's an attractive interaction between the two, and these Cooper pairs are basically like once you have the condensate of these Cooper pairs, that's what causes the superconductivity. So now, why you can have this, why electrons typically have opposite charges, and so they don't like each other, so they like to repel each other. So it's because these electrons, as they move through the superconductor, they actually do some distortion of the lattice or whatever of the phonons, and there's a sort of like a phonon-mediated interaction of electron with an electron through this deformation of what's happening there. So BCS theory, you have basically condensation of Cooper pairs. Which are like electrons. And so basically you can, how much, you assign to this something which is called microscopic wave function. Microscopic wave function psi, which is like it's a complex number, and if if the magnitude of this psi is non-trivial, then you say, well, I have this these Cooper pairs, and this is I have non-trivial condensate of these Cooper pairs, and so the phase transition between the superconducting and non-conducting phase is if this is a temperature over this is a temperature, then I will have some critical temperature. The psi will be 0 here, and then there will be a second order phase transition here. Second order phase transition. And here you will have non-trivial condensate of these Cooper pairs, and here you are in the superconducting phase. So basically, below critical temperature, this is working, and you start condensating these things. It's a second order phase transition. It starts from 0. If it started from non-trivial value here, there will be a jump. There will be a first order phase transition. But now this is nice and smooth, and it's a second order phase transition to superconducting phase. Okay, so that would be the microscopic theory. And so once you have this condensate, everything what I'm describing there it sort of starts happening. What we will be much more interested in is the phenomenological description. So the phenomenological description is provided by Landau-Ginzburg theory. So has this been actually reviewed in PSI, during PSI? Yeah, it has. So that will be a very quick repetition of what's happening there. Okay, perfect. That's great. It was during statistical physics, or perfect. Perfect. So basically what you do is that you write down like a function, effective field theory description, Landau's function. And in this case, it looks like this thing here, m star, h squared over 2m star. Then you can have some fluctuations of this psi. That's why I'm adding like a derivative term, psi square, and then you have a psi square b over 2 psi to the 4 interaction, and then you can add the electromagnetic field. And so this is your Landau's function. when you first discuss second order phase transitions, you probably didn't have this in homogeneous terms. So if everything is homogeneous, you just have this and that, and you vary with respect to these things, and then you get where where the phase transition happens, and it's some A over B term over here. So here the DI is just the gauge covariant derivative, DI minus I E star AI over H bar, and then it's a Cooper pair, so it's 2 electrons, and the effective charge is again 2 electrons. All right, so that's such a simple theory actually can describe the superconductivity. And so how does it work? Is well, this psi here is this complex quantity, and so what you do is that you write this psi as the magnitude, can depend on x, magnitude E star phi of x divided by H bar. So you basically divide it as a phase and the magnitude over here. Okay, and then once you do that and you plug it over here, something interesting happens. That will be the last long formula, I hope. So then if you plug this into this Landau's function, you find that this L is just given by h squared over 2m star. Now di of this magnitude square, and then E star square over 2m star psi square di phi minus AI square, and then A C B over 2 psi to the 4 and 1/4 Fij square. Okay, so this is what happens, and that's will be crucial for our discussion. And let's denote it by star. Yes.
So typically when I form a bound state, the total energy of the bound state is smaller than the sum of the masses, of the rest masses of the constituents. So why here the effective mass is exactly equal to the electrons?
That's a good question. These actually. So I would certainly claim that it's 2 times the charge, right? But the question is like, I mean, effective energy will be definitely small. I agree with that. I don't know. All right. So we have this Lagrangian here, and now look at what happens. So specifically, you can look at what happens first when AI. So by the way, we have the gauge potential A mu, and the A mu. So here, these I things, they are just spatial indices. There's no time dependence here. So we'll be working in a gauge where like A0 is equal to 0. I don't know, it's called radiation gauge or something like that. So anyway, so this is like a spatial index. So now there's no electromagnetic field at all. And if AI is equal to 0, then if you look at what we have over here, then we have some kinetic term for the phi, right, for our phase, but there is no any mass term for the phi. Okay, if you look at that here, then you see that phi actually is like a massless and Goldstone boson. So phi is the massless Goldstone boson. And it precisely, it corresponds to this phase. So if it takes some value here, then you're spontaneously breaking the U1 symmetry, the rotational symmetry over here. So U1 symmetry breaking. on the other hand, if you have vector field, then something interesting happens. So now AI is not equal to 0. But then if you look at what's happening inside that bracket, we have AI, well, minus partial I phi. Well, that looks almost like a gauge transformation. So if phi is a gauge, then this looks like a gauge transformation. So in other words, if I choose a gauge transformation, I can kill this phi and I can absorb it into AI. Okay, so in this case, phi can be absorbed by gauge transformation to AI. So it's obvious, like it's just a gradient of my gauge function. But now if you look at that, what happens then? So this term just becomes AI square, right? But I have kinetic terms for AI, which are over here. That's just the Maxwell thing. So there's something times AI square, which looks like a Procard theory, like a massive vector field, right? So in this case, AI is massive. And so what we basically describe is just the Higgs mechanism, right? We just eaten our Goldstone boson, and then we have massive. So it's like Higgs mechanism. And we have massive vector field. And then if you look at that, what that mass is, so typically what you would write is like a kinetic term plus m square times AI square or something like that. So whatever stands in front of this AI square is like the mass of the of this vector field. So I can write m a square, and so if I do it the other way around, it will be like m star divided by e star square psi square. And of course, this defines a length scale. By the way, you can expect, like if you had the homogeneous phase, you can write this thing here. You wouldn't have the derivative term there, and it would just be given by A over B. It's not important for us. So anyway, this thing here defines an important scale. So 1 over mass square is a scale lambda square, and this lambda is called penetration length. As we shall see, this is precisely the length, how far the magnetic field can go inside the superconductor. Okay, it's precisely this lambda, and it's related to the mass of this vector field. You know that if you have massive things, then you have exponential decay instead of 1 over r thing, and then so you have penetration length. And you know, it would be like the W boson mass or whatever. Yes.
So what happens with the x dependence?
Sorry, what happens with?
Psi square depends on x, right?
Right. So what I'll be doing this is I'll be replacing, it's a very good point. So I will be replacing this with the approximate homogeneous value. So the homogeneous value would be like I am extremizing this without the kinetic term. Everything is nice and homogeneous. And then this psi square is something like A over B. So what you really mean by this thing here is something like psi is A over B. So you take it as a constant here. Yeah. It's a good question. So very good. So now we have one mass or one length scale associated with this mass of the vector field because we have eaten our boson or whatever. But there's of course another mass, which is the mass of this condensate psi. So you see there is a kinetic term for the psi, but there's also a massive term related for the psi. It's like A times psi squared. So now what you have to do is that you have to move these things to the mass, and so there will be the other scale. So there's another scale, m psi square, and that's given by 8 square over 2 m star a. I'm just moving, whatever is there onto that, and that gives you this psi squared term, which is a correlation length. So we have two length scales. One is the penetration length, it's related to the mass of the vector field, and the other one is like the mass of the psi, of the condenser, and that's related to the correlation length, how things are actually spatially varying, okay? Very good. And so now, depending on what is the ratio of these two lengths, you can have either type 1 or type 2 superconductor, okay? So, so depending on the ratio of these two lengths, so we can have psi over lambda, and it's either bigger than square root of 2 or it's smaller than square root of 2. I don't know why square root of 2. So anyway, so this will be type 1, and this is a type 2 superconductor. Okay, so now what's happening with type 2, if you look at that, what are we saying? We are saying that the psi is actually smaller than lambda. Okay, what does that mean? Is that the penetration length is bigger than the correlation length. So actually, for type 2 superconductors, the magnetic field can enter the superconductor. Okay, so here, magnetic field can enter the superconductor this is done via vortices without destroying the superconducting state. So actually, you know, like here, the magnetic field really can penetrate. It's done like through these, you know, vortices, which you probably discussed in statistical physics as well. But it doesn't destroy necessarily the superconductivity. Only when the magnetic field is very, very large, it will destroy it, the superconducting state. But here, basically, you are saying, well, I cannot have magnetic field inside at all. Here, I can have, and it enters through weird way. But if the magnetic field is too big, it will destroy the superconductivity. And so the holographic superconductors are precisely these type 2 superconductors. Okay, so this is what people were able to do. Holographic superconductors are type 2. Okay, so this is good. So one last thing I want to mention is so-called London equation, which is again a trivial consequence of our star equation over here. Okay, so what is London equation? Is that you take the star equation here, you treat it as a Lagrangian for your theory, and you just vary it with respect to the vector field AI. Okay, and you do it so AI is non-trivial, so I can already absorb my phi into that, and so then it's obvious that I have the massive term here for AI square, and I have the kinetic term over there. So if I vary it with respect to the vector field, I just get massive vector field equation, Procka equation. Okay, and that's what's called London equation in this respect. So this is like a massive Procka equation and so you get it by doing delta A in the star equation in the gauge where you absorb the phi inside. And if you do that, then you just get the Maxwell equation with the mass Tj F Ji, and then the length scale, the mass, is given precisely by this penetration length 1 over lambda square, right? So it's plus 1 over lambda square AI is equal to 0. Okay. So that's what's called London equation. It's just, a consequence of the fact that now vector field is massive. If the condensate is non-trivial, if psi square is non-trivial, then the vector field is massive. Otherwise, it's massless. Okay. And so, what are the immediate consequences of this? Is that basically you can derive first the Meissner effect, and you can also derive the diverging DC conductivity from this equation immediately. Let me just show it to you. Okay. So once you have this equation, that once you are in superconducting state, once you have non-trivial condensate psi, right? Then my vector field has mass given by this 1 over lambda square. So what are the consequences? Okay, so consequences. Should I do it here, maybe? So immediate consequences. Of this London equation. So first would be the Meissner effect. So you just consider the vector potential, which gives you the BZ vector field. Okay, so you consider AI to be 0, A y of x, and then 0. So that's your vector field that gives you the magnetic field in the z direction. And so if you look at that, then we have di fi, and I take the non-trivial component to be y. Okay. And so I, the only non-trivial component here of fi y is x. So it'll be fxy. So this is t x f x y. But fxy will be just a derivative of ai with respect to x. And I'm differentiating again with respect to x. So it will be two derivatives of that. So it's minus d square x ay. But from our Procca equation, this is equal to minus 1 over lambda square ay. Okay, and so if you integrate this, well, you have two derivatives acting on something is something, well, it's constant times that something, so the solution is an exponential, right? And so there will be the exponential decay, which is your favorite. So if you consider the BZ, the magnetic field, which is precisely this fxy, right? Then this is equal to B0. Well, okay, let me write one more. dx ay, and that's some B0 e minus x over lambda. So you see that really the magnetic field is exponentially decaying as it tries to penetrate the superconductor. Okay, so it's this exponential decay, and you see that the length is precisely this penetration length, and so really it can penetrate only very little, and then it exponentially decays inside the superconductor.
How about positive?
Sorry, positive?
Yeah, you can also write the solution each to x over lambda.
It will be exponentially diverging. Well, yes, but that would be unphysical. What would, yeah, I don't know. What would stimulate that, right? With an exponentially growing field. I don't know. You're right. Okay. The second is diverging DC conductivity. So how would we do that is, well, when I look at this equation here, you could also, so this is like a massive, there's no current here. It's like a massive vector equation, But in principle, nobody can prevent me from putting this term here on the right-hand side and call it a current or something like that. Okay, so if I call this minus Ji, everybody should be happy. Okay, why not? So what you can do is that you can take the time derivative of this Ji, and it's minus lambda square dt ai, right? That was my definition. Okay, so that's in the x space, but you can do it in the Fourier space. So you can do the Fourier transformation. So the time derivative will just become, so now I consider a as a function of omega. Well, so j something like that. That's your Fourier transform, and similarly for j and for a and everything, right? So if you do that, then if I differentiate this thing here, I pick up minus I omega j of omega, right? So we'll have minus I omega j of omega, and then I have minus 1 over lambda square. But recall that when you want to form the electric intensity from the vector potential, it's just given by the time derivative of the vector potential. So this thing here with a minus sign is just a EI, right? That's how the electric intensity is defined in terms of the vector potential, right? So this thing here is like EI. And you can do it in the omega space as well. And so you get an amazing formula that Ji is, well, it's minus 1 over lambda square I omega EI, or it's I over lambda square omega EI. But if you recall the Ohm's law tells you that this should be equal to sigma times EI. So this is Ohm. And you see that the conductivity sigma, the imaginary part of sigma, goes like 1 over omega. Okay, so that means the real part of sigma will be a delta function, and we just proved the diverging DC conductivity. Okay? So basically, you see that everything follows from this phenomenological Landau-Ginzburg theory, and I guess you have done this in your statistical physics course, right? Perfect. So that's just a repetition. Let's just jump into what we need to do to construct the holographic dual for that. So first, why are people interested in these things? Is that there's something which is called high TC superconductors. TC superconductors. And so these are very, they are 2 plus 1 dimensional, it's like these plates of these superconductors. They are really like 2D rather than 3D. And so they are interesting in that as the title says, that the critical temperature below which they become superconducting is quite high, right? And so there are sort of like various estimates for which the BCS theory can actually work. I think it's like 30, 40 Kelvin or something like that. So you can describe by this, BCS theory, by the weakly coupled thing only when the transition temperature is about 30 Kelvin. But these things have 100 Kelvin, and they can have almost room temperature superconductivity. You can almost see, right? So dimensional cuprates, and they have high TC, which is actually bigger than 30 Kelvin, for which the BCS theory cannot work. Cannot describe. And people believe that they are also strongly coupled. And as such, they should be an ideal candidate for you to study them by ADS-CFT, right? So yeah, should be ideal. CFT. All right, so that's the idea that maybe you want to apply ADS-CFT to describe these very strange materials, which you cannot describe, which you don't have microscopic description by a known theory. All right, and so in order to start discussing this thing here, we want to build the ADS dual. So let's build ADS dual. And so the first part, let's say we need some ingredients. Okay. So what are our ingredients to start building a phenomenological model for the superconductors, right? And so first of all, well, we want to talk about superconductivity that's at finite temperature and stuff like that. So you need an ADS space with a black hole. The black hole will provide your temperature, right? So we have finite temperature, finite T. So that means we have a black hole. So we need to consider an ADS spacetime as a black hole. Now, because we want to describe 2+1 dimensional theory, where your theory is like really on the plate or whatever, right? So the black hole will be 1 dimension higher. So we want a 3+1 dimensional black hole, but we also want to preserve this plateness or whatever. So the horizon of that black hole will be planar horizon. Okay, black hole in 3+1 dimensions. But we want a planar horizon. Planar horizon. Okay, so that we actually preserve the symmetry of this 2+1 traits or whatever. Okay, so we have so that's what we seek. So now, that's the first thing. Second thing, if you look at this thing here, this is very interesting. So we already know that there are some phase transitions for black holes. We discussed many times the Hawking-Page phase transition or whatever. This was the Hawking-Page phase transition, like that. But what happened here is that we had the free energy which was continuous, but the derivative wasn't. And so that corresponded to the first order phase transition. In other words, what was also happening is that there was like a phase transition between radiation and large black hole. I told you radiation is only a little bit of radiation, doesn't have much entropy, whereas the black hole, like the first lecture, has lots of entropy. So here, the entropy jumps like crazy. Okay, so there's a first order phase transition, entropy jumps, right? On the other hand, here, we want to describe a second order phase transition. In the second order phase transition, the entropy should be actually continuous. Okay, so we want continuous entropy. Want second order phase transition So continuous entropy. Okay, so what does that mean? So we want a situation where we start with a black hole, and then something happens to the black hole which describes a second order phase transition. But we have to end up with something which is comparable entropy. And again, it's finite temperature, so we have to end up with a black hole again. So it must be a black hole to black hole phase transition where something happens, so it cannot be a radiation to black hole or whatever, it must be a black hole to black hole phase transition. So we seek black hole to black hole second order phase transition. Okay, so this is what we want to have. But now we can be much more specific. So what's really happening in this superconductivity here is that you start, well, if you are above Tc, there is no condensate. If you are below Tc, there is this complex condensate in your system. Okay? So how you describe the simplest thing is that, well, this is described by a complex number. So the simplest holographic dual will be complex scalar field. Okay? And so what we really want here to build is that we start with a black hole which for temperatures greater than Tc has no scalar field, and for temperatures smaller than Tc has a non-trivial scalar field condensate around the black hole. Okay, seek black hole second order phase transition. Condensation of complex scalar field. Complex scalar field in the bulk. So in other words, our phase transition which we are seeking is a phase transition from black hole which has no scalar hair to black hole which has a scalar hair below critical temperature. Okay? Now, if you ask people 20 years ago, they will immediately tell you this is impossible. Wisdom is that this is impossible, as we have no hair theorems. So in other words, we have a happy black hole here, and that's possible, but we cannot have a black hole which would carry some hair. So that's not possible, okay? So that wisdom actually is not true. You can have you can have hairy black holes if you are in ADS. So these no-hair theorems, they always work like, yeah, well, considering this configuration of I don't know, Einstein-Maxwell theory, right? That's within the frames of Einstein-Maxwell theory. Can I have like Maxwell hair, or can I have something non-trivial happening with the black hole? And then you will find no, the black hole is only characterized by mass and charge, right? And then nothing else can happen. And so then you can go theory by theory, prove case by case. This is possible, this is not possible, and stuff like that. That's where these no-hair theorems come from. But people didn't care about ADS black holes, right? Because, well, who cares about ADS black holes, right? But nevertheless, in ADS, this is possible. You can have scalar condensate in ADS black holes, and so this is actually not true for ADS black holes. And this was first shown by Gupser, I think 2000 something. You can have hairy black holes if you are in ADS. In fact, you can have hairy black holes in asymptotically flat case as well, but the theory must be much more complicated or whatever, right? But here you can just have a scalar field. Okay, so very good. So now we can describe our condensate. If this is a possible, and we can describe a black hole which doesn't have hair at high temperatures, but for small temperatures, it has actually hair precisely like this. Then we are very happy, right? Last thing which we need, though, is that we need to really, we are interested in the response to electric field and stuff like that. Right, so we want to know what is the conductivity, and so that's a current related to the electric field. So the last ingredient which you need to consider is also you need to put the electric field in the bulk, so that you can study the response of the system to the electric field. We also need a mu field in the bulk to study conductivity and stuff like that. All right, and so these are really basically the ingredients which you need to build a holographic superconductor. So you need to have the condensate that will be described by scalar field. You need electric field to study the response to the electric field, right? You need a black hole to have it at finite temperature. And that's it, right? So here's the theory. So there's an H cube theory. H cube stands for Horowitz, Hartnell, and somebody. Herzog, maybe? Is it Herzog? Yes.
What assumptions of the theorem are violated in AES?
Say it again. What
Assumptions of the Noether theorems are violated in AES?
I guess it has to do with the asymptotics. Like the asymptotics is very different than the asymptotically flat case. But as I say, even in if you start putting weird scalar fields in the asymptotically flat black holes, like if you start putting some weird potential and some weird things, yes, you can have hairy black holes even in flat space. But it's just crazy theories which people haven't considered before. So really, you have to prove case by case, theory by theory. Can I have hair or?
Yeah, probably you violate some energy conditions, as you're saying. But in here, you're not going to consider high curvature corrections?
No. It's just yeah. So I will just write the simplest thing here. It will be just Einstein-Hilbert plus scalar plus electromagnetism. So here, they wrote this thing here. So this is our action, d4x square root of g, Einstein-Hilbert with negative cosmological constant. You put the electromagnetic field Fmn square, and then you put the complex scalar field psi with some mass like that, and here this covariant derivative again is the covariant derivative with the vector field. So this dm is just the covariant derivative nabla m minus ea am. Okay. So that's the theory where you can get basically something like holographic superconductor. It's the simplest thing you can write down. Okay, and so basically the idea is to take this theory and construct something like a hairy black hole for t smaller than Tc, and then normal black hole, like no hair black hole for t bigger than Tc. And by hair, I mean the scalar field condensate around the black hole, and that's really possible. Okay. So very good. So let's do this in the simplest possible setting. So we see that we have all these field content here, but the simplest thing would be let's fix the background. Okay, let's forget about these fields here for the moment. Fix the background, and then consider the fields living in this background, like test field approximation. Okay, so let's do it. So let's just do simplest thing is to do test field approximation. And so we will take the solution of the gravity sector completely separate. So if you just have Einstein-Hilbert, you want the planar horizon. So the solution will be Schwarzschild ADS black hole with the planar horizon. Okay, so we have Schwarzschild, so the background is the Schwarzschild ADS4 planar black hole. So now you know how to write it. We derived it last time, except we just have we had ADS5, Schwarzschild planar black hole last time. So now it will be ADS4. So you just go one dimension lower. But let me use the original coordinates. So instead of z, they use u. It's basically like z, but rescaled by something. So you see that it's almost what we derived last time, but not quite. R 4 1 over. So u would be like z, u square minus f dt square plus dx square plus dy square. That's our planar horizon. And then plus L square du square f u square. Okay? And then this f is 1 minus u cube. And then u goes from 0 to 1. 0 is the boundary. And 1 is the horizon. Okay, so basically it's what we have derived last time, except there's some strange prefactors R0 over L floating around, right? So what we would have in our case would be like 1 over z square minus blah, 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 and then we would be plus dz square over f in the bracket, right? Anyway, so this is what they write down. And so now let's take this as a background. This background provides you a non-trivial temperature, gives the temperature, which is like 3 0 divided by 4 pi L square. So that's the corresponding temperature of this black hole. That's the Hawking temperature of the black hole. Okay. And so now let's study how these vector fields, the vector field A mu and this scalar field psi behaves on this background. Okay, so I just used basically you use this your Lagrangian that gives you the equations of motion in this background here. Okay, that's the test field approximation. So let's do. So we have ingredients. That's our theory. So second, let's study the phase transition. And so what you can show is that the vector field is always given by this formula over here. This is just the test electromagnetic. So U is 1 over R. So this is like Q over R of Reisner-Nordström. Okay, so I'm just taking that as a test field. Instead of Q, I'm writing this mu or whatever. Right? So this is Q over R. Just the standard electrostatic potential, and then you shift this by 1. Why not? So that it on the horizon it vanishes. It's just a choose of gauge. Okay, so that's the vector field which we'll be taking for now. And the question is like, what's happening as we start changing the temperature of the black hole? Meaning as we start, making the black hole more extremal or less extremal and stuff like that. Well, okay. So that will be in the back-reacting case. But yeah. So what's happening with the scalar field here? But before we do that, let's just look at the mass of this scalar field. Okay. So note that m square of the psi effective. Okay, so if you look at this Lagrangian here, well, it's given by m square, that's the bare mass here. But then if I expand what this covariant derivative here is, then well, you have normal derivative there, but you will have also the vector field a mu times psi. So it's like a mu square gives you a correction to that mass. That again gives you the psi square term, right? So it's plus g mn am an. So that's your correction due to that non-minimal coupling there, right? Okay, and so what you can show is that this is equal to m squared minus mu. Now I'm plugging this a is this thing here, so it'll depend on mu, and then this g depends on some parameters, but I can express it in terms of the t. So instead of writing r0, I'll be writing t. Okay, so then you can show that this is equal to mu over t squared, and there is some function, not this one, of u, different function, but the function is positive. Okay, that's what's important. Okay, now look at that. So we have the effective mass coming from this coupling with the vector field and stuff like that. It's given by the bare mass minus something positive here. Okay, so it happens that at some point this thing here. So in other words, if it depends like what is the ratio between mu and t, how much negative this thing will be. If I am at very large temperatures, if t is really large, so t large, then really, you know, this m squared dominates, and I'm subtracting a small number, right? So then, okay, I didn't tell you what this m squared is. Let me write that first. Okay, you will play with this in your tutorial on Friday. Okay, so you will see that a very cunning choice of this bare mass is actually the following one. Now you will stone me to death. M squared is minus 2 over L squared. That's a cunning choice. Of bare mass. And you will meditate about this in tutorial 6 on Friday. Okay, so you will basically derive why this choice of the mass is the right choice of the mass you should be considering here. So now, why you will stone me to death? Well, this m squared is negative, right? So negative m squared typically not allowed, right? So that's true in asymptotically flat case. In asymptotically flat case, you cannot have stable fields if they have negative m squared. Okay, if you are in ADS, you can have negative m squared, and it can still be stable. But it cannot be too negative. There's something which is called BF bound. Again, you will derive it in your tutorial 6. So this is still like larger than BF bound, and your field is still stable. Okay, so this is larger than some bound, larger than BF bound. I'm already spoiling your fun in tutorial 6. And so it should be stable. So the wisdom here is, if I am in flat space, if I have negative m squared, it's a disaster. It's an unstable situation. Something bad will happen. Okay. If I'm in ADS case, I can go a little bit negative, and it's okay, still stable. But if I go too negative, again, disaster will happen, and something is unstable. Right? Okay, so this thing here is still stable and should be okay. But now look at that. If I have the effective m squared here, well, it's this thing which is still stable, but I'm now making it more negative here, right? So in particular, if I take t really small, okay, if I take t really small, I'll be subtracting a huge negative number. So for if t, what did I say, is small, it's much smaller than mu, yes, then m effective square is really much smaller than 0. And then, something bad will happen, and instability will happen. Instability will happen. And we will have scalar field condensation around the black hole. On the other hand, if t is much larger than mu, then I'm subtracting a really small number here. It's basically like this m squared. I'm in a stable situation, and I don't have scalar here. Okay, so really, like it depends on the temperature. For small temperatures, I will have a hairy black hole. For larger temperatures, I will have the normal Schwarzschild radius black hole. All right. So now, what really happens if you do the calculation? So you will find that if t is bigger than some Tc, then you find that indeed psi equal to 0. So this psi here satisfies the corresponding equations of motion. It satisfies some second order differential equation, blah, blah, blah. Right? So if t is bigger than Tc, you'll find that the solution of the differential equation is psi equal to 0. If t is smaller than Tc, but not too small, then, as I say, like psi satisfies some ODE. The details of that ODE are not important. What you do, as you always do in the ADS-CFT, you look at the boundary. So near u equal to 0, which is the boundary, you find that this psi behaves like psi 0, u to delta minus, plus psi plus u to delta plus, where these delta plus and minus are your favorite deltas related to the mass, as we talked about them like 2 weeks ago. These are the scaling dimensions of the thing. And in our case, you will find that delta minus is equal to 1, and this is equal to 2. If you use the formula which I provided you a couple lectures ago. So there's this delta plus minus is d over 2 plus minus square root of d squared over 4 and stuff like that, which was exactly the same formula. So now we know this is the source for the operator O, which is dual to our bulk field psi, right? That's the source. So now what we want is we want spontaneous symmetry breaking. Okay, so we don't want to have any source for this. So we are setting this to 0 by hand. That's our boundary condition, so that we have spontaneous symmetry breaking. It's not induced symmetry breaking. It's a spontaneous one. Breaking. Okay. And then this thing here is the expectation value of that operator. Okay. That's the second thing. Very good. So now what you are basically trying to do is that you have some ODE for psi, and you impose a boundary condition. Psi 0 is equal to 0, and I'm interested in this thing here. And you solve your ODE numerically. And when you solve your ODE numerically, this is what you find. So numerical solution gives you that T over Tc is 1, that's the critical temperature. This is how the O expectation value of the operator, this psi plus, looks like. And you can even find that it's actually T minus Tc to 1/2. There's a critical exponent 1/2 here. So you indeed find a second order phase transition with this critical exponent beta equal to 1/2. And since I'm running out of time, let me just mention that if you want to calculate, so indeed we have a phase transition. There will be a condensation of the scalar field around the black hole. It will be a second order phase transition. This condensation of the scalar field will induce the expectation of value of the boundary operator, and then this is how it looks like through the standard ADS-CFT dictionary which we discussed before. And so if you wanted conductivity, So if you wanted conductivity, then what you need to do is that you need to introduce a time dependence, but also you need to introduce like the electric field. So AXU e to minus I omega t. Then again, so this is your ansatz on top of your electrostatic thing. You are putting this AX here. Okay, and then again, you write down the equation for AX. You expand it at infinity, close to the boundary. You look at the expectation value of that. That's related to the expectation value of the. You look at the right fall off, this one here. That gives you the expectation value of the current on the boundary. Okay, and then you can relate this expectation value of the current to the electric intensity through Ohm's law. It's sigma times E, and from there you can read what the sigma is. Okay, and then indeed you find that in this case the imaginary sigma goes like 1 over omega if t is smaller than Tc. Okay, and so you find indeed infinite DC conductivity here. So let me stop here. So indeed, you can play with this simple model. You see, it's like super simple model, right? The gravitational thing is there's this question: should I go beyond Einstein-Hilbert, right? Yes, you can go beyond. You can consider higher curvature corrections. You can consider like people typically like Gauss-Bonnet corrections, which originate from string theory and stuff like that. So people keep playing like with this model, but this is the simplest thing you can write down. But already this simple model, you can basically derive all features of superconductors. Right? You have second order phase transition from non-hairy black hole to hairy one at small temperatures. You can show that this behaves as it should and gives you the right critical exponent. You can show that indeed DC conductivity diverges. What you can also show is that if you start putting a magnetic field, then here you would also put, so this thing here now, if I'm putting the magnetic field, it will have the component GTT AT squared, but it will also have GII AI squared, where AI is a magnetic field. So now this thing here, we calculated here, there was a negative contribution from this piece here. But this thing here is positive. So if you have magnetic field, then this thing now effective path will become positive, and there won't be any instability. Okay, so then if you're putting the magnetic field there, you destroy superconductivity. Okay, so you can sort of check also a feature of the Meissner effect and stuff like that. So let me leave you with this. I think it's amazing, and again, it's like very, very simple calculations telling you about these high TC superconductors, which nobody really understands what's happening over there. Let me stop here. Questions? So you will play with these things a lot in the tutorial 6, where you will, meditate about this BF bound and why it has to be negative and what's happening there. Okay. Question? No.
I mean, this is very cooked.
Sorry? This is
very cooked. Like
cooked.
You chose everything so you can match the same.
This is the simplest model you can cook up. Yes, I agree with you, right? And then it doesn't come from any deep theory or whatever. It's just like what I need to make this happen.